and it is connected to the utility grid to the substation, and central power plants are connected to that along on the transmission system. Now, what is a micro? What are its subsystems? A microgrid consists of set of local loads being fed by one or more local electric power generators like renewable energy system based or diesel engine based or combined heat and power or captive power plants. Like if there is a steel plant, also microgrids. Steel plants, you find that there are steam turbine based power plants of the order of 200 megawatts, up to 200 megawatts or 250 megawatts. So these power plants, so it makes the local loads independent of the utility grid power. At the same time, if the utility grid is not, if the local load is not sufficiently enough for meeting requirements central power or the captive power plant, they also feed power to the utility grids under a power purchase agreement and all those things. At the same time, in case the local captive power plant is not able to meet the full load requirement, the local distribution network, then power is drawn from the utility grid. These are the various aspects. We'll see more of it in the next slides. Then there is a new type of energy source, which is called as micro turbines. Hello, are you able to hear me clearly? Professor? Hello? 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 Coordinator, please.
Sir, good morning, sir. Yeah, we are hearing, sir. Here.
Okay, fine. Sometimes I'm finding voice quality bad or something. So,
no, your voice also clear, sir.
Okay. Now, the need for microgrids and benefits from microgrids. That briefly, I'm showing a few of them. Economics is the main advantage of the microgrids. Then we have that how it gives more economic benefits. We'll see in the next few slides. Reliability of electric supply to local loads through local generation. And it can also feed the local load without the need for power from utility grid during natural calamities. Then the microgrid can be used to generate. Microgrids can be installed with new energy sources which are more clean, which provide clean energy like renewable energy or alternate sources like microhydel, mini hydel. This can also be networked. It all depends how the configuration of your microgrid is. Then we have other advantage of microgrid. They're generally having a lot of sustainable energy sources. Again, the renewable energy sources like solar, wind, then sometimes other sources like battery energy sources. So we have another advantage of microgrids is that their cost of generation of electric energy is lesser than the utility grids on the present days. So that is another aspect. So in this aspect, I would like to bring to your notice recent large-scale solar power plants, solar parks, quoted to the NTPC and other government organizations that they can supply per unit of electricity at the rate of 2.50 rupees approximately. Whereas the power produced from the thermal power plants, large thermal power plants like the NTPC and all, is costing around 3 rupees discoms or to the transmission system, our national dispatch centers and all those things. So we are seeing there's a lot of downward trend in the cost of electricity production through renewable energy sources. Now that trend may continue further, and we are going more into the clean and sustainable energy sources. Then these microgrids also provide us with a lower time to erection and commissioning. So they come into the revenue production mode much faster than conventional coal-based thermal power plants or hydro-based power plants. You see, a conventional 500 megawatt thermal power plant takes around 3 years to complete the commissioning and installation from the date of technically clear commercial order. And that means its gestation period is over 3 years, whereas a 1 megawatt or even 5 megawatts, the solar power plants can be 6 months time nowadays. And I was told by the single largest solar power plant in AP, that is the Greenco, their head of the organization, works organization, he told me that around 800 megawatts they installed in less than 1 year. So the fast turnaround time, that means going into revenue production mode is very fast with solar power plants today. And compared to a conventional thermal plant, they are able to give you power within 1 year, whereas thermal power plants take around 3 years. So that much time, that means their 2 years generation money is available to the independent power plant producer, IPPs. Then excess power in the microgrid not used in the local grid can be exported to the utility grid. Reduced transmission losses, large energy savings. So as the generation is within the local grid, so we don't have the transmission losses by drawing it from a faraway center. So that's another advantage. Then one more advantage of microgrids that they provide is peak load on the utility grid is also reduced. So these are the aspects which are very important and very beneficial by having microgrids. And microgrids are becoming more and more widely used worldwide. And this slide shows another detail of a microgrid. It's an illustrative one. Now if you see here, the conventional substation is connected to the utility grid, and the distribution transformer from the substation feeds the local microgrid. For example, your college is also a microgrid when it utilizes a DG set as well as a solar power plant and any other energy sources if you install in the college. So if you see, the important thing is the point of coupling between the energy source and the utility grid, this point of interface, POI, point of interconnection, is a key point where it is connected to the utility grid through a breaker. Now, in this slide, we have to take into consideration a few important aspects or key factors of microgrids and utility grids when they are connected to utility grid. Now, if you see here, this is a typical example of a microgrid where there is a combined heat and power plant which has got a thermal storage, then there is a gas turbine, then there is a local grid in this feeder. Similarly, we have another feeder here, another feeder or a bus bar, where we have a solar power plant along with a storage system, and then we have wind-based power plant, then we have a number of local loads, and there's a battery energy source. Now, the important concept that has to be taken to mind by looking at this microgrid is our renewable energy sources also. The renewable energy sources are non-dispatchable generation, whereas the conventional centralized coal-based generation or hydro-based generation are dispatchable generation. As you all know, in power systems, dispatchable generation means the output of the power plant can be controlled to give as much designated power as required. Whereas from an installed capacity. For example, you have a 500 megawatt thermal power plant connected to the utility grid. If the load is not there, you can reduce the output of the power plant. If the load is more, you can operate at its full rated power plant output. Whereas in a renewable energy system based power generation like solar power plant, the installed capacity, for example, is 1 megawatt or 100 kilowatt like in a college. It cannot be controlled unless the input source of energy, that is the solar radiation, is available. Similarly, a wind power plant. In a wind power plant, the wind energy is the driving force for the wind turbine, and it depends on the various weather conditions. So this type of power generation through renewable energy sources or through any source where the operator does not have control on the output production of the power, this is called non-dispatchable generation. And also the load managing system cannot stop that power unless they sink it at the source of the energy source. That is, for example, solar power plant, you put a big dumping load and then dump it. So the most important thing here we have to see is these are in the context of these distributed energy sources connected to a microgrid or to the utility grid, the dispatchable generation and non-dispatchable generation mode of sources of energy. Similarly, we have here controllable loads and non-controllable loads. So most of the loads we can have lighting loads as controllable loads. For example, you have critical loads like servers. There we need a load which cannot be shut down. These kind of things are there. Then we have in a microgrid, the microgrid control system and an energy management system. So the microgrids operating modes can be said to be in two modes. Microgrids can operate in two modes. One is grid connected, other is grid independent or local mode, which is also called as island mode. Then there are various issues like reference voltage under island mode. See, for example, in some of the colleges where I worked after retirement from BHA, the management used to think that having a solar power plant is just like a UPS. And they were feeling when we have installed a 100 kilowatt solar power plant, why we have to run a DG set when the utility grid fails. The issue, as you all know, is that these solar power plants work along with the utility grid's reference voltage. So when there is a reference voltage, then the solar power plant will be up and it will start pumping power into the local grid or utility grid. Now when the utility grid is off, it doesn't have a reference voltage. Then what we do here, we put the DG set under light load condition and take the local grid voltage as the reference voltage, and the solar power plant wakes up and starts giving supply to the local grid. We'll see other issues, how it is also having variations in the next few slides. So this is another important mode. Today we are having solar power plants with special power. One minute. So there are special power conditioning units in solar power plants where they can operate the solar power plant in grid independent mode, that is island mode also. But they have their own advanced features and there are certain limitations also. Then the main advantage of microgrids, as we have seen earlier, from the environmental point of view, they contribute a lot of benefits in terms of use of renewable energy sources, which are sustainable energy. We don't depend on the fossil fuels like coal, oil or gas. And Most important thing, they relieve us from the stranglehold of certain energy source producers like oil-based production, or like, as we all know, crude oil we have to import for India. So these things give us energy independence also by using more and more renewable energy sources. Now, clean energy also is available through renewable energy sources integrated into microgrids, and these reduce pollution and reduce pollutants. So the main pollutants of the coal-based energy sources like thermal power plants are particle matter, carbon dioxide, the nitrous oxide, and sulfur oxide, sulfur dioxide or something. So these are also reduced because we are using wind source or solar energy, or maybe biogas, or like as I mentioned, heat produced from solid waste in the metropolitan areas and other places, and other sources. Now we have other benefits of microgrids: the reduced use of land, water as compared to coal-based power plants. See, for example, the coal-based power plant uses whole acres and acres of land. It also needs a lot of continuous supply of water for cooling the condensate water and other, the boiler output water and other, and the steam turbine output water. And for those heat exchangers, we need a continuous stream of water and source. We find that's why a lot of power plants having cooling towers and other places. Whereas in a solar-based power plant or a wind-based power plant, we don't need water except for certain maintenance purposes. And this releases of dependence on the water, which is becoming more and more scarce. So this is another one. And the land requirement for a solar power plant, as you must be knowing, is for about a 1 megawatt power plant, solar power plant, we need 5 acres of land. So this, even if you take at 800 megawatts, it becomes relatively less compared to a big thermal power plant. Now we have other aspects of microgrid which we would like to see, that is disadvantage of microgrids. The interfacing with utility grid of the for the microgrid poses certain problems and issues arise out of those interconnection. So the utility grid faces a special issue with the integration of renewable energy sources which are non-dispatchable in nature. That the net load to be met, it becomes a duck belly curve where it requires fast ramping up or down of the coal-based power plants, which are majority of the power is supplied today in our utility grid through coal-based. So we'll see more of this in detail in the next few slides. The renewable energy integration issues like regulation, 80% of the capacity is only allowed nowadays at the distribution transformer level to install a renewable energy source. That's why you see, if you're having a college and you want to install large solar power plant, it is not allowed by the DISCOM. They see that the issues related to over penetration, that means over installation of installed capacity, higher installation of installed capacity of solar or wind-based power plants, doesn't give problems of control of grid, utility grid, because of the non-dispatchable nature, sudden fall or sudden rise of output of the renewable energy source-based power plant. So there is a norm that is brought out by various DISCOMs. They are now implementing that 80% of the transformer capacity of the load transformer capacity can be connected with a renewable source-based power plant like solar or wind. Then microgrid protection is a major challenge. Again, here we see this issue is a separate subtopic by itself. So I'll just highlight certain things. Like earlier, the circuit breaker used to have unidirectional flow of current. Similarly, relays also used to have unidirectional current. Whereas today, with local distributed energy resources connected to local grids, at time of short circuit, there can be a large bidirectional current flow. So these things need to be met with a new type of alternative solutions. Then there is a fast changing of local generation due to variation of weather and climate affecting the renewable energy generation. So as we have been discussing earlier also, the source of energy for the solar power plant, that is the solar radiation, or the source of energy for the wind power plant, the wind, cannot be easily controlled by us. It depends on the various weather conditions. So there can be sudden rise or sudden drop of power from these sources, which are again the issues which require attention in the grid integration or local grid management. This will result in large swings of active and reactive power generated in microgrid, resulting in fast changes in grid voltage, apart from other issues. Now, there is a amount of rationalization being brought and certain amount of standardization being brought for interconnecting issues. When we are connecting the microgrids or renewable energy sources with the utility grids by following certain standards which will specify certain standard operating procedure or standard installation procedure. So like lower interconnection problems are likely if complied with IEEE interconnection standard of IEEE P1547, which is evolved. But today the Central Electricity Authority in India specifies for Indian conditions to interconnect renewable energy systems at the utility grid level, IEEE 519, which is an older version. It's being replaced by IEEE P1547. The major reasons to build a microgrid, as we have been discussing, they are economical to operate a group of local loads and local generating sources, draws low net power from utility grid, reliability of power supply to local loads when utility grid supply fails through islanded operation or through grid independent operation. Utilization of clean energy or renewable energy based power sources, as we have discussed, all sources like solar and other sources, wind and other sources. Then major reasons to build a microgrid are they are smart and decentralized distribution networks. Why we call them smart is all microgrids must have energy management system. This energy management system will schedule the loads and power generation and drawing of power from the utility grid, and so it manages the supply and demand equation or a demand requirements in the microgrids as well as the utility grids. And there are many more reasons. So I have specific opinion that these microgrids have many applications in India, especially in rural areas, along with distributed energy resources, and also very important in remote areas where utility grid power supply is not available. Now, this is a typical example or illustration of an energy hub system which some other countries are having, and we may also have it. So if you see here, we have a AC utility network supply, and it is coming to local center, load center, and from there it is also have in this it also has a DC microgrid, that is an AC microgrid. That means after the distribution transformer, we have a set of loads and set of distributed energy resources. So here you can see wind power plant is there. Then we have solar power plants, integrated PV solar. Then we have other sources like the electric cars. These electric cars, when they are not running, their batteries pump power to the grid. So they are connected to DC grid, again they are connected to. So this is a typical new format of a micro grid. It is being evolved. So if you see here, apart from building loads, we have various other new types of energy sources. This is only for illustration. Now let us see another illustration of a microgrids. See, in the US, the Navy has converted a offshore campus of their Navy installations into a microgrid. This shows an illustration. This illustration shows how a conventional load center can be converted into microgrid and made independent of supply from the utility grid. So here it's typically in this south site in Minnesota, USA, they have installed from the standard loads to the local distribution network a small wind turbine based power generation, solar power plants, then battery energy storage system, then a diesel generator, then micro turbines. So these micro turbines are a new type of turbines where the chemical energy, just like steam, instead of steam, any fuel, chemical, which has got a chemical energy, it runs the something like gas turbine. It of lower capacity, generally it is lower capacity. It turns the chemical energies by burning the gas fuel, it becomes gaseous and runs the turbine. And these turbines are available right from 2 kilowatts to 200 kilowatts, or even 500 kilowatts, or even at megawatt level. So this enables a portable type of operation. I'll try to show some photos if possible. So diesel generators, as you know, conventional standby power in all places, and these are the various types of distributed energy sources connected. And this grid is also connected to a utility grid through a suitable interface. Then types of loads, if you see, we have office space, which is non-critical load. Then we have critical loads like data centers, which are need to be provided continuous supply of electricity, and for a transient movement or for a limited time, the critical loads can also be supplied with a UPS. For a longer time, some of these sources feed local grid. And there is a big office establishment which houses various number of persons and other facilities. This energy management system microgrid will have to plan well, and the microgrid generally help. Their function is to schedule the power out, so distribute energy source to meet the total local load. Another important aspect of energy management system in a microgrid is power will be imported into the microgrid from the local utility grid. So the total local power generated is less than the total local load demand, and power will be exported from the microgrid to the local utility grid if the total local power generated is more than the total local load demand. In many microgrids, the energy management system enables microgrids to produce excess power and export it to the utility grid. Thus, so this enables the microgrid operator or the management to earn revenue or have almost zero net power drawn conditions many times from the utility grid. So the power drawn from the grid is minimized or have almost sometimes zero power drawn. This also saves a lot of cost and energy for the load centers or to the microgrid operator. Especially when there is a time of the day tariff, price for the energy consumption from the utility grid uh, is also a benefit. That means there are, in India we are not having it, but in some countries it is there, the time of the day tariff. That means during the peak times there is a higher tariff than the off-peak times. For example, from 10 o'clock to morning 6 o'clock, the tariff charged by the utility grid managers or the distribution network is that which is having a lesser rate than the standard peak load or daytime tariff. So people schedule the loads like battery charging of the electric vehicles or other loads. Sometimes industries, they take benefit of it and produce their output or use it in the non-peak hours at lesser tariff charges. So this saves money. So this facility also is beneficial for the microgrids operators who can manage through the energy management system affected the loads and also the distributions. And the power generated in the local grid through distributed energy resources can be used to feed the power to the local loads during the peak time and take the power from the utility grid if necessary at the low tariff time, that is time of the day tariff prevalent conditions. These are the major financial benefits to the microgrid operators. More details are not presented here due to limited time available in this webinar, so other details can obtain some other information. So this is just to give an idea that these are the main advantages of microgrids. Now let us see why I am telling all this is we have today the topic of energy sources for microgrids and utility grids. How the need arises for a energy storage system and for a utility grid system. So if you see here in the microgrids, is again this is an illustration to show the power generated and consumed in a local microgrids. This corresponds to this data corresponds to the Navy site in Minnesota, which is published, and this is a very good illustration and to understand how the microgrid is operated and controlled. So if you see here, this data shows the load which is shown in this arrow mark with a blue color. The blue color, it is the local load. This is the load. Now, in the microgrid, in this microgrid, we have various sources of energy, distributed energy sources, like the red color one is a micro turbine. This is feeding this much amount of load at this time, and the x-axis shows the time of the day. From midnight, from a typical day, from midnight to next day midnight. So 24 hours, it shows how the load and energy source outputs are managed in a microgrid. So the y-axis shows in the units of kilowatts. Now if you see here, the base load is met by the micro turbine, just like similar to a thermal power plant meeting the base load. And if you see here, the peak curve is coming from 8 a.m. to almost like 5 p.m. and then going down. And this is a typical curve in the particular load distribution center, load center. And here, how the microgrid operator is managing is he is seeing that base load is met by the micro turbine output, which is controllable. Then we have, that means dispatchable generation, the concept which we learned earlier. Now the non-dispatchable generation, which is solar and the wind also maybe. So solar is meeting certain peak part of the load in this total load curve. Similarly, battery is also designed to meet a certain amount of peak curve. Then we have the dispatchable load here. So these dispatchable loads are shown in black color. These are the things. So this can be switched off or switched on depending on the. Now we have one more important thing is now this total load, because it is met by majority of portion by the local distributed energy sources, the imported power from utility grid has taken a lower level. If you see this red curve, red line, it is imported power from utility grid. Now this, if you see, it is at a lower level, and what it shows is, if the local distribution is not there, distributed energy resources are not there, this line, imported power from utility grid, would have been same as the load curve to meet a load balance, supply and demand balance. So you see, this is the gain which we have by using local distributed energy sources instead of the conventional power from a utility grid. This is the point to be noted. How this is going to be advantageous, we will see later. Now, here I am showing a typical solar power plant of 100 kilowatt output rating installed on a rooftop type, a single line diagram. This is for your information to understand the various features. Some of these kind of solar 100 kilowatt peak rooftop mounted solar power plants may be there in your colleges, or it may be having higher ratings or lower ratings. So if you see here, the important thing here is, I could not show in an enlarged fashion. This is a your interconnecting transformer, that is your receiving transformer distribution level, and it has got a, this is the transformer, sorry, it's very mildly shown here, and it has got a bidirectional energy meter. Earlier we used to have a unidirectional energy meter, which used to only measure the power drawn from the utility grid. Now with the distributed energy resources connected to the local grid, it becomes microgrid, and we have the facility to pump power back to the utility grid if the local load is not sufficiently meeting the output power generated through the distributed energy resources in the local microgrid. So for this energy meter had to be made a bidirectional meter. So this is the importance of this particular thing, and this is a typical configuration where we have 250 kilowatt modules for a solar power plant, and this is 100 kilowatt, so mostly around 400. See, for every 1 kilowatt you need 4 panels. 10 kilowatts 40, 100 kilowatts, 400 panels you need roughly to get 100 kilowatt power. So this is the typical system, and you have here a string type of inverters which are connected to a group of solar panels which are called arrays, and these arrays are connected to a 33 kilowatt inverter, and this is also another 33 kilowatt inverter, and this is also 33 kilowatt inverter. They are tweaked, that means little bit adjusted for one of them to make it 34 or so, and then make them into 100 kilowatt. So of course there are some ratings 27 kilowatt, but they have been revised later to 33 kilowatts. These are something like Fronier's company, or today you have other companies which are popular in the market. So that shows a typical single line diagram where the solar power plant is connected through string inverter to a local AC bus, and the local AC bus has got again various control, and that is connected to local grid. Okay, so now if you see this kind of typical solar power plant shows an output in a day which is varying in nature because of the incident or radiation. Now this is an actual graph of output production in a typical installation in Hyderabad in 2018, and it shows the power output from the 33 kilowatt inverter, which is part of the 100 kilowatt, one of the in the 100 kilowatt in solar power plant, is rising from morning 5:30 and going up, peaking up. It's peaking between something like 8:20 to 2:30, or roughly 3 o'clock. Let's say 8 to 3 is the maximum output from there. From there it is going down. By 5:30 it is having zero output. Now what this shows is that there are a lot of variations in the output of the power plant, of a solar power plant. This is a typical one. Now let us see, these variations create problems to the end user as well as to the grid manager when they are connected to the grid, utility grid, or even for the microgrid. Now this typical 100 kilowatt solar power plant rooftop day-wise output for a month, in the month of September it is showing, from September 1st to September 30th, you can see that the power day-wise is varying. Each color denotes the power output of one inverter. Depending on where the solar panels are falling, suppose there is a cloud, the particular inverter output is affected if that particular panels are covered by cloud. If that's why you can see certain variations from this installation of the particular solar inverters output. So this is to be noted again. Now this is again shows a month-wise variation. This month-wise variation is important to us to tell how the weather varies over a year. So we cannot expect from 100 solar power plant 100% output every day, every month, every year, throughout all the months. Throughout we cannot expect, throughout the month we cannot expect, throughout the year we cannot expect. So these are the variations of solar power plants. Now let us see how these variations can be met through a new method, that is using energy storage systems. Before we go there, if we can understand more of these concepts of microgrid, which is important, through some videos. I would like to show a few videos. Hello.
Hello.
Are
Yes,
you able
sir.
to see my the
Yes, sir.
video? Are you able to see that?
Yes, sir.
Yes?
Now we are able to see your presentation.
All right. Now, are you able to hear the sound also?
Yeah, your audio is clear, sir.
Not mine. The video which I am showing here.
No, sir. No video, sir.
No video. So I have to see that wherever you are giving me this upload facility, I must include the total screen instead of the window application.
Sir,
Please help
sir,
me in that.
Sir, are you using a browser version or a desktop app version, sir?
Desktop version.
Desktop app version. If you are sharing, sir, while before sharing, it will ask include system audio, sir. Before sharing,
yeah, I have not included.
You should include the system audio, sir. Then it will show the video as well as the audio, sir.
What I'm supposed to do now?
Stop the screen sharing,
Okay.
sir, and start once again. Start once again. Before starting, include the system audio, sir.
Include system. All right.
Yes.
Now I should go into this more. Are you able to hear anything?
No, sir.
Okay, let me see. No?
Hold on for a minute.
Sir,
yes,
it is
sir.
coming slow, but just increase the system value.
Okay. This is 100%.
Okay. Okay.
Are you able to hear anything? I am not able to hear.
Once play the videos.
Now it's Is it coming?
Yes. 1 second.
I'm not hearing the sound.
Yes.
Okay, let's see this, then we'll go to the other one. These are all 1 minute, 2 minute videos. So this Microsoft one I have not used earlier. So
Very slow in this other one.
hello. Hello.
Hello, sir. Sir,
Any video sound?
1 second, sir. No, sir.
Okay. Okay. Let's try with other video. Just see the visual only. I will see if there's any issue with the. Actually, it gives a lot of sound. I don't know why. Okay, let's. I'll try to show another video.
Sir, if you could please switch off your mic and then share the video, sir.
I tried that also. I'll try another video. Let's see. Now?
Yes, sir.
Generally speaking, Hydro-Quebec's hydropower generating stations
Yes, sir.
and grids
Can you able to hear
supply the homes and
Fine.
a microgrid can be set up by adding technologies such as solar panels, large capacity batteries, and electric vehicles connected to electricity use. Microgrid technologies can supply homes and businesses in parallel with the Hydro-Quebec grid. If the main grid goes out, the microgrid can continue to supply power to homes and businesses for a while, keeping customers comfortable. When the sun is shining and less power is being used, the microgrid can supply the whole neighborhood or part of it. And if the microgrid generates more electricity than the neighborhood needs, the surplus can be fed back into the Hydro-Quebec grid. Microgrids, an energy solution for the future.
Okay. I will show a little bit one more so that there are all very small videos, but very illustrative.
I'm Kelsey
Are you able to
Misbrenner
hear?
with Solar Power World. Today, we're in Pittsburgh at the Eaton Power Systems Experience Center.
Hello? Are
Yes,
you all
sir.
able to
Yes,
hear
sir.
the video? Right.
Yes, sir.
Okay,
Yes.
I'll continue.
I'm here with Dan Carnevale, who can tell us a little bit about microgrids. So Dan, what do you do at Eaton?
Thanks, Kelsey. I'm the manager of this facility we call the Power Systems Experience Center. And each year we bring about 6,000 visitors through, everybody from fifth graders to CEOs. We talk about electrical things. We actually show them how electrical things work and sometimes don't work. So in this case, we talk about this system behind us here, which is a microgrid.
So can you tell me what a microgrid is?
Well, a microgrid is basically a smaller version of what the utility power system is. So think about if power goes away, you want to have safe, reliable power and also efficient power. And we find that a lot of our customers, military bases, hospitals, and even parts of utility systems already have assets in place, basically maybe solar, some storage, and certainly a lot of generators out there. So a microgrid is combining all of those systems together with the brains to make it work efficiently, reliably, and safely.
So how might this be useful, especially for a military base who rely on the power?
Right. Well, a military base, especially, it's all about resiliency and reliability. We have to make sure that if power goes out, power is available for them when they need it and as much power as they need. So it's about storage, it's about other sources that come from a local source, for example, generators on site and maybe wind and solar that's stored in batteries.
And what does Eaton do with microgrids specifically?
Well, what we do is we tie all those assets together. So our purpose in life, I guess you would say, with microgrids is to take the existing assets on site or new assets that we design into a system and put the controllers and everything that makes a microgrid work together. So if we do that well, a customer doesn't know if the normal system on the emergency system or on solar power. For example, this system right behind us here, we have 4 different sources of power. We have a generator, we have the utility, we have solar, and we have batteries. We could very easily add wind or any other mechanism to provide power, but all of those systems work in conjunction with each other. And what Eaton does is we take all those systems, tie them together with our Power Expert energy optimizer, and make those systems work again seamlessly, so the end user doesn't really know where the power is coming from, but they have continuous power, reliable and efficient power.
That's great. Can you tell me the different parts of the microgrid behind us?
Sure. The first part is the utility piece that comes in, and basically that's whatever the service entrance requirement is in terms of amps and volts. We provide that, and we help the customer make sure that it's the right size for their system. The second piece, in our case here, we have a generator, and that's backup power, and we need to size that according to the worst case scenario. So if they need to be islanded, for example, and run only on that generator, we can do that. The third piece, in our case, we have some solar power. Now, the solar is obviously only available during the day, and sometimes maybe even overproduces. So what we'll do with the solar is we bring it into the fourth piece, which in our case are the batteries, and those batteries then charge and discharge according to, when the solar is available and when power is cheap, so that we can kind of levelize both the load, but also where the power comes from. And really, it makes it more efficient and cost effective for our customers.
Awesome. So why did Eaton get involved in the microgrid technology in the first place?
Basically, we have a field service team that's about 1,000 engineers across the country and across North America. And basically what we do is that expertise that we have, tens of years of experience in each of those engineers that go out and do these installations, really provides the background and the knowledge to bring that power into our customers and actually do it in a safe and reliable way.
Well, thank you so much for your time, Dan. This has been a great experience. Where can people go if they want to learn more about this center?
The Power Systems Experience Center's website, and the easiest way to look it up is eaton.com/experience.
Great. And for more videos on microgrids and all things solar, visit solarpowerworldonline.com.
good grammar and spelling are important. Want essays that in messages that
With 60% of the human population set to be living in urban areas by 2030, and pressure on regional and national power grids continuing to grow, a number of cities are now turning towards localized energy production for new developments. As the name suggests, microgrids are small-scale electrical networks that operate independently or in tandem with large-scale electrical supplies. While many national and regional electrical grids are now powered in part by renewable energy, the majority still depend on nuclear and fossil fuels to deliver the bulk of their power. Conversely, microgrids make heavy renewables, such as photovoltaics and wind turbines, to generate energy for use within a specific building or development. This enables them to power their systems and operate without adding to the demands of the wider electrical network. On-site energy production and storage can enable a new development to become self-sufficient and help fill in the gaps that can arise on overstretched electrical grids. As part of their pledge to honour the 2016 Paris Agreement on climate change, cities around the world, including several in the United States, are passing legislation to make all new public buildings and developments emission-free. The use of microgrids can contribute significantly to achieving these requirements, whilst better insulating large urban areas from potential power failures or blackouts. Excess energy generated on small-scale systems can be stored on site for use at a later date, or be fed back into wider power grids when necessary. Whilst legislation is one step, private enterprise is also getting on board with microgrids and localized energy production. Pursuing clear environmental benefits and reduced operating costs, developers are beginning to integrate systems from forward-thinking manufacturers and technology entrepreneurs alike. One such manufacturer is Polysolar, a UK-based firm who have developed transparent photovoltaic glass. Their panels can be used to cover large areas without obstructing views and resemble conventional windows. Though currently emerging, this system could be adapted to cover larger glass buildings in cities around the world, allowing them to generate much of their own electricity. On a more domestic scale, Elon Musk's Tesla solar roof integrates photovoltaics into conventional appearance roof tiles, turning entire surfaces into localized power generators. This system is integrated with the Tesla Powerwall, allowing excess energy to be stored and used throughout the year. Many large and small-scale developments are also now incorporating wind turbines to generate power and feed their microgrids, reducing their reliance on regional and national power networks. Energy market analysts Pike Research estimate that microgrid power generation has now increased 5-fold from 2012 levels, and with an increasing array of innovations coming to market, we could see entire cities and urban areas powered very differently in the years ahead. If you enjoyed this video and would like to get more from the definitive video channel for construction, subscribe to the B1M.
Okay, so we have seen a few videos on how the microgrids and what they are, how the microgrids work and what they are and what are the benefits, apart from what we have learned in the earlier slides. So some advantage we have is they show large material in short time. That's how I adapted the videos, since we don't have a physical meet now. So I thought this is the best thing. Now we'll go to the next section. That will be energy storage systems in microgrid applications. Would you like to have a break now or later?
Yes, sir. Yes, sir. So with your permission, we would like to take a break. I would like to announce a break of 10 minutes.
Right then. Fine.
Yes,
so we'll start the next section on energy storage systems in microgrid applications after the break.
Yes.
So thank you for your
Yes.
patient listening till now.
I request.
I'm putting my mic in the mute.
Yes. I request all the participants to take a break, and we will resume the session at 11:35. We will resume the session at 11:35.
Okay, thank you.
Yes, sir. Thank you, sir.
Hello.
Excuse Rajagopal sir.
Yes, I'm ready.
Welcome back, sir. We would
Thank
like
you.
you to continue with the sessions.
Right, I'm starting now. I'll
Okay,
share
sir.
my slide. I'll switch off my video so that right. Whenever you don't hear me, just tell me. Right. Okay.
Okay,
Now
sir.
I'll go into presentation mode. Okay. Are you able to see the video?
Yes, sir. We are able to see the presentation.
See the presentation.
Yes.
Right. We are going to start the second section, that is energy storage systems in microgrid applications. So
Sir,
you have seen the yes.
excuse me, sir. Can you minimize the box, sir? Black box which is on the bottommost right corner.
Yeah, this if you want me to minimize. Okay.
Yeah, just
Right.
minimize. Yes.
Right. So we have seen the requirements of a microgrid and the benefits and applications, and we have seen them at length. Now we'll see energy storage system applications in microgrids. See, in islanded mode or isolated microgrids with high penetration of RES. This means that we are not connected to the utility grid. There is large amount of supply for the local grid, local microgrid through renewable energy systems based power sources like solar, wind and all. Apart from energy which meet the base load like diesel engine based DG sets or any other gas turbine based and all those things. So in this condition, energy storage systems can provide ancillary services like frequency and voltage regulation. Energy storage systems combined with renewable systems based on solar or wind can be designed to provide continuous power output and stable local grid system operation. Now, when these energy storage systems operate in fossil fuel based microgrids, their energy storage systems can considerably reduce fuel consumption. This is achieved through the energy management system of the microgrid. This energy management system can be designed to use energy from energy sources, energy storage sources as much as possible, and then only use the fossil fuel based DG sets output. So this can be programmed in the energy management system. This will reduce the runtime of the fossil fuel based DG sets. So this is the major applications of, and these are the major applications of energy storage systems in microgrids and their benefits. Now let us see some illustrations how these energy storage systems applications are being used in a total power system in an advanced network. This slide I am showing from the literature published by ABB. So it is a industry practiced topology. It's not just a theoretical one. It's industry practice topology. So if you see here, the conventional central generation based coal-based power plant is connected to a transmission system at 220 kV through a local 20 kV bus through various step-up transformers. Here, energy storage system is used in this power. This is a typical example, illustration. Now, it can be different for different applications. But I found that this is a very, very illustrative for various applications. Load leveling for generation utilization, load leveling applications for generation utilization is the target of this energy storage system design. That is, they have rated it for 100 megawatt for 4 hours. Similarly, at the transmission end to other loads, here again energy storage system is used for spinning as a spinning reserve in case of line loss up to a capacity of 10 to 100 megawatts and time supply, that is energy, this power can be supplied over a period of time from 0.25 hours to 1 hour, depending on the design of the system here. So this is another application. Then we are coming to renewable energy generation sources, which are connected to the grid at 220 kV or so. Then here they are connected to the 100 kV local AC bus from a 20 kV one through step-up transformers. Here, the purpose of this energy storage system or the design objective is integration of renewables to give a steady power to the grid so that the grid is not affected. That will be, here they have designed it. This can be generally used from, this is generally used from 1 to 100 megawatts capacity, and a time span is 1 to 10 hours. So next, in this particular network, that means we are coming towards the load side. Now here is a typical distribution network we are getting from transmission system. It is stepped down 100 kilovolt kV, and then it's connected to a local grid in this. So here at the beginning of the step down transformer, that means on the HV side, this energy storage system is used for frequency regulation. The power rating generally at this point will be around 1 to 50 megawatts, and the duration for which this power has to be supplied can be planned from 0.25 hours to 1 hour. Now, then we are coming to the local loads and local generation systems. Now here we are seeing that at the LV side, 20 kV side, we are having energy storage system applications where its function or design objective is to meet the load leveling for postponement of grid upgrade, so that power that can be supplied is 1 to 10 megawatts for about 6 hours. So this postponement of grid upgrade means we can reduce this local grid capacity increase by providing a local energy source. So we don't draw the full, so this much power is reduced from drawing from here, otherwise we would have increased this local distribution network, transmission network capacity. Now, so here the purpose is postponement of grid upgrade and load leveling. Now here when we are coming to the actual load application point, where the energy storage system is used for peak shaving, that is peak demand to be reduced from 0.5. This supply is designed to be from 0.5 to 10 megawatts. Energy will have, that means power, how much time it has to be supplied is energy. That is 1 hour. So this is the typical energy storage applications in a large power system as well as in the microgrid. So this local industry with a local distribution network is what we have seen earlier, microgrids and all. So energy storage systems have large applications in microgrids as well as in utility grids. That's the point to be noted. The benefits of these energy storage systems are power system load leveling, deferred network and generation investment, grid stabilization, increased use of renewables, grid compliance for renewables and generation systems, power quality improvement. Power quality improvements means we all know it is basically we are talking regulation, frequency regulation, and harmonics reduction. So features from these energy storage systems, what we can generally design are: allows a range of energy storage devices to be coupled to the grid, dynamic power control, that is active power, then dynamic reactive power control, that is Q control and P control, generator emulation control mode, grid stabilization features, synthetic inertia and active damping, high and low voltage right through. This is an important feature, LVRT, which are being insisted by the utility grids and local discoms to be provided within the renewable energy sources total capability. So that can be met through parallel adding energy source for that particular part. Black start capabilities. Black means when there is no grid supply in the network, then you should be able to start or when the renewable system is starting from the cold start. That is a black start supply. Modular inverter blocks for simple long-term maintenance, built-in module redundancy without interruption or operation. That is maintenance aspects. We have options: islanded mode, which is IEEE 1547 compliant. Then we have enclosure options. These are all what they're giving for the mechanic. This is typically, this is how it looks. A cabinet mounted, I mean, something like a portable container mounted energy storage system made by ABB, just to get you an idea that how things physically look. Now the internals of this energy storage system, this is power conversion system, which is the name given for this particular energy storage system. I mean, this typical name for this. Now here, this shows a single line diagram. What we see here in this power conversion control system or power conversion system is we have a power converter section as well as an energy storage section and a control section which controls the power converter output. Now this energy storage system here is a battery energy storage system. This battery output is connected to a inverter or a bidirectional converter. Basically is the bidirectional converter, and in any bidirectional converter, you know, there is a power flow from the AC side to DC side and the DC side to AC side. So here the power converter is a DC to AC converter or a inverter when it's operating in the inverter mode. It is a AC to DC converter, that means a control rectifier when it's operating from AC to DC. Now this is connected to a step-up transformer, a suitable transformer to local grid or to the microgrid. Now here you see here the battery energy storage system output is DC. This is converted into AC and then fed to the grid. Now when the battery needs to be charged, you take power from the grid, feed it to power converters and feed the battery to get charged. Now this is a typical energy storage system interfacing to AC grid, and then how it is. We have various control. We have you measure the input voltage through VTCT and then grid power flow control with grid losses and all are detected. Various signals are taken, and then we have here again a breaker which connects the grid to this load. At that point, this energy storage system is connected through a power conversion system. That's all. And balance are all control element, these control circuit elements like we have here a DSP and other things. And this particular slide shows it can have a modular power conversion from 1 to 16 modules depending on the capacity. They can plug in and increase the capacity. And we have a GUI where it shows the various parameters required online and all. Then there is other features. So we are not going deep into it, but just have an idea. This is how it looks in a single line diagram. The function of a power conversion system. Now this system is a typically ABB one which I am showing. Its model is PCS 100 system. They can be paralleled. Now I'm just trying to show you this typical specifications, how industrially they manufacture and supply, and whereas commitments and parameters monitored and delivered within a particular range. So this can be made from 52 kVA to 2800 kVA. That means almost 3 MVA per single system. Now utility voltage, any LV or MVA voltage standard voltage tolerance plus minus 10%. The output should be frequency can be between 50 to 60 they can supply. Frequency tolerance has to be plus minus 5 Hz. Power system type transformer coupled. These are all various. Then you see here current harmonic discharge should be less than 3% at rated power. What we generally think is the THD has to be throughout. It is not throughout. At the rated power, the manufacturer delivers less than 3% THD, total THD of current THD. All these other things are fault capacity and all. Then efficiency is greater than 95% at rated power. This is important again as the power converter design topology selection point of view. Then overload capacity 120% for 10, 100% 30 for 30 seconds, 200% for 2 seconds. So all the rating selection of the power converter power semiconductor switches. As you all know, the power semiconductor switches don't have overload capability. Hence, they have to be rated for a full load capability for even for the short line currents required from the power conversion equipment, power converter. The important thing we have to note here, the energy storage system is generally, this power has a DC bus range, that is a window it is called, 200 to 820 volts. So the energy storage system has to be designed to have a DC bus output voltage, which can be operating in this variation. Then there is another type of power conversion equipment which is having 1000 volt range. Then it has to be from 750 to 1100 volts. So these are the things, important things which we should know from the point of battery bank or energy storage bank system design point of view. That's it. Okay, these are the things show other parameters to be met and all. I'm not going into the detail because of the time. Now, energy storage applications in microgrids, we have seen at length in the first slide. So these are all put in a little bit more pictorial form. And this is based on the white paper published on electric energy storage systems by International Electrochemical Organization, IEC, in December 2011. By mistake, it has come one extra, should be deleted. Now, if you see here, as an energy designer, we will be looking at how much power the energy storage system should give for how much time. So power is V into I, how much power we should. How much time we should give is energy. So power is in watt and then energy is in watt hours. So if you see here, from our point of view, if I am trying to design an energy storage system, I must know for what purpose it should be designed and how much duration. So these are generally frequency of, they give the typical applications, how much in a day, how much time I had to design my energy storage system. So we have seen what is power, wherever the energy storage systems are kept for what functionality in the earlier slides. So this is energy shifting, that is you shift the solar power output. I have showed you the solar power output from 100 kilowatt typical power plant. The same is there for 1 megawatt also, depending on the landscape. So if you want to give the solar power coupled through the energy storage system like battery storage system, you can shift the energy availability from the total pack, that is solar power plant plus energy storage system, to give a combined power which is beyond the normal simple solar power output only. So this is called energy shifting application. Try to grid forming applications. That is, when there is a sudden dip or a particular network fail, it should be able to still give some supply. It should not trip. These kind of things are there, and durations are shown here. These are all renewable integration issues. I'm not going detail into it because of time. Should have got a lot of other more presentation material. So integration issues I'll briefly touch in this section. This material I got from one of the workshops I attended in the Institution of Engineers. So RES and utility grid integration issues are forecasting for scheduling and dispatching, then flexibility in conventional generation, including ramping up, reactive support, transmission system design criteria, reserve and standby capacity, storage, and costs. Okay, these are all various forecasting mechanisms are there for wind and solar. You can see that what are the issues related to this renewable energy based power generation. And then why I showed this particular thing is we should understand a typical solar power curve. If you smoothen it, it will be looking like this. Solar power plant output curve. It will be something like a smooth bell, inverted bell curve. It's a bell curve, and that means from morning 5 to evening fired, you can expect the output of the solar. Whereas if you see, this is a typical wind generation trend in a particular area where it's almost like reverse of the solar. So this shows good potential to take this energy and store in an energy storage system and feed it to them when they require to make totally both of the energy storage system and wind or solar together giving a steady power output. And let us see how it's done later in some of the slides. So this gives some other issues related to grid integration. Threat to grid security with the renewable energy system base. I just want to give an illustration which is quote. Now if you see here, it illustrates on 1st July 2014, due to sudden wind generation loss, Tamil draw utility grid increased from 3,340 megawatts to 4,560 megawatts. So the power flow on a 765 kV network between Solapur and Raichur 1 and 2 increased from 200 to 1,050 megawatts each. This led to SPS of solar of this SPS of 5 kilowatt solar Raipur line, but operated, resulting in load shedding in southern region amounting to 605 megawatts. This is a practical case which was recorded. What it shows is the sudden rise and fall, a sudden fall of generation from a renewable energy source has resulted in the stability issues, major grid. Now, that's one point to be noted, integration issues. Now, this point I have to highlight because with energy integration, the utility grid would have met the actual demand in this particular fashion, including this red curve. Renewable energy penetration, that means we install number of solar power plants or wind power plants. These are, as we have discussed earlier, their generation from the load dispatch center point of view is that they cannot be regulated. Hence, they have to be given first priority in evacuating power from their power plants. So the load will be met by, in this particular case, by the installed renewable energy sources which are having sufficient wind or solar radiation. Hence, the net load that has to be met by conventional power plants has fallen to this blue line. Hence, the gap between the actual and net load is what is met by the renewable energy based sources. Now this curve, what it shows is these dispatchable generation units like thermal power plants or even hydropower plants. Yes.
Excuse me, sir. Sir, we are unable to see your. There is no change in presentation, sir. We can only be able to see only one slide, sir.
Yeah, I'm explaining the slide.
I'm only seeing one slide, sir, which is written as energy storage system in microgrid application. That's it.
So
there is no curve, sir. Sir, could you?
So far, you're not.
Sir,
so far, you're not seeing anything.
Yeah, no, sir.
Last.
I thought you were orally explaining, sir.
No. I showed so many slides. You missed all slides.
Could you please stop sharing, sir, and share once again? Sir, now we can able to see, sir. Now there is a change in slides.
My God, I have. This is the only slide you're seeing.
No, sir. Now there is a change in slide. There is something written today.
This also showed. Is it not there visible? Hello.
Hold on for a minute, sir. Yes, sir.
If you don't see a slide change, please let me know, because I'm not able to see what I'm presenting because I'm seeing only the window which I'm seeing here. One of you please monitor.
Okay.
All these are important slides. You have not seen that. I'm explaining all those things.
Sir,
Okay.
sir, don't show in the slideshow mode, sir. Just share the PPT, sir.
This is not the mode you want.
Just share the PPT, sir, in this mode.
I've been doing that only.
But there is no change in slides, sir. We can able
This
to
slide,
see.
this slide I have been explaining for last 5 minutes. This slide, particular slide. Okay, now let me see if you don't get the next slide change. We'll come back to that. You monitor me.
Yes.
Let me complete this presentation on this particular slide. Now I'll check up with you if the slide has not changed. So now what we are seeing is actual demand is this curve, which is also joining with at this portion, and
Sir,
this is the
sir,
net load met by the. Tell me.
There is no curve in the slide, sir.
Are you able to see slide presenting expected all India duck curve?
No, sir. The slide is just has one title. That's it, sir.
What is the title?
Energy storage system in microgrid application.
Maybe I have to I will try to reboot again and see what is
sir,
that.
please
I don't
stop
know why
sharing and start. Yes, sir. Now we are able to see the curve, sir.
But I am not able to see. So how to? I'll do one thing. Stop seeing. I'll do. Then open share tray. I'll go to this. Now you see. Are you able to see the slide?
Hold
Hello?
on. Yes, sir. Yes, sir.
Okay. Expected all India duck curve. You're able to see?
Yes, sir.
Okay. Whenever you find some difficulty, some of the participants or you should coordinate and tell me. Okay.
No.
If there is no slide change, come back to me. Otherwise, I will be speaking with not effective way. You think I'm just delivering a lecture. All this I made only to show that it comes to the audience visible. Right. So, is it clear? Expected all India duck curve slide you are able to see?
Yes, sir.
Yes.
Yes, sir.
So now, as I've been explaining, the red curve is the actual demand in this portion is deviated from the. See, actually, the red curve and blue curve overlapped up to here. From here, the red curve is the actual demand, and it again gets mixing and going. What does it mean? The blue curve is deviated from here and reduced. This is the actual net load to be conventional thermal power plants or hydropower plants in the grid together. Now, the difference between the actual demand and the net load is the load met by the renewable energy based sources, and that is varying. So hence, the net load that has to be met by thermal power plants or base load plants is the actual load minus the power generated energy sources like distributed energy sources like wind or solar power plants. So sudden dip and again sudden rise. This is called a duck belly curve. So here it is estimated to be in this shape, and this is also published in the site National Load Dispatch Center SCADA data. This is combined. This cumulative average, this annual growth rate curve. So you can see this. So this portion, sudden portion, low portion, and rise is called duck belly curve. And the significance of this curve, this denotes that the thermal power plant's output has to be suddenly dropped and suddenly raised, which produces lot of stress on the generators. So this is the point to be made. Okay, then I'm not going into these text slides. Impact of renewable energy integration on utility grids. Are you able to see this slide? Hello? Hello?
No, sir. We can.
Are you able to see this?
We can only be able to see the previous curve, sir. Belly curve.
I don't know what's happening. Some connectivity issues. Right, I'm running short of time also. Now are you able to see impact of RE integration utility curve grid?
No, sir. Yes, sir. Yes.
Hello?
There is a little delay, sir. Yes, sir.
Should I again go up?
No, sir.
No?
We can able to see the impact of RE integration of utility grid, sir.
But that's not on full scale mode. No, it is on not slideshow mode. It is.
Yes, sir.
See
Normal.
now. Now is it able to? Are you able to see?
Not on the slideshow mode, sir. Just a normal window. We are able to see, but it is neatly, completely visible, sir.
No, if you
Clearly visible.
want, I can log off and then come back. Just that's the only alternate I can do. That is Microsoft principle of all delete and reboot. Okay. So I will just read out. At least you are able to see the slide. Impact
yes,
of
slides
impact.
and also the latest.
Okay. There are various issues related to RE integration on utility grids. That is, conventional grids are designed, operated and protected on the basis of unidirectional. With RE integration, that is renewable integration with the utility grid, we pose there many problems, including a few illustrated below, like fault clearance, reclosing after fault, inadvertent island operation, then injection of harmonics into microgrid and utility grid, voltage dips, over voltage, and voltage flicker. I will not go into details of these issues. We'll go quickly into our energy storage system issues. All these are illustrated in this slide. Are you able to see this slide?
Yes, sir.
Now you see,
there is a change in slides.
Now you see?
Yes, sir. It is a table, and now it is a block diagram.
Now are you able to see the block diagram energy storage system implications?
Yes, sir.
I think earlier you missed when I started the lecture and explained everything in detail. Okay, this is the conclusion part. Let us say this is again a summarizing part of the energy storage applications in utility grids. So if you see here, energy storage systems are connected in the typical topology of energy storage system introduction, major power system. This is this slide I taken from the publications by AB. And here if you see, the energy storage system applications have at the central generation plant near the 220 kV transmission line starting. Their purpose is for load leveling for generation utilization up to 100 kilowatt for about 4 hours. This energy storage system will be designed. So that means the function application of the energy storage system at this point, transmission line beginning point is for this purpose, load leveling. And as you know, central generation output is connected to the transmission line through a step-up transformers. The local bus at the central station will be power station with 20 kV, stepped up 220 kV. At the end of 220 kV transmission line, at the receiving end, just keep a watch on this slide. If you don't get this slide visible, please tell me. Okay.
Okay, sir.
So this is an important slide. At the end of the transmission system, the energy storage system has an application taking care of spinning reserve in case of line loss. That power generally is designed for energy storage system output power is generally designed from 10 to 100 megawatts, and duration for which this power can be supplied can be planned from 0.25 hours to 1 hour. That is about 50 minutes. This is another application. Now we have energy storage system applications at the renewable energy sources connection to the utility grid, that are at the micro. So if you say in this case, it's at the utility grid at megawatt level, solar parks and other places. Now here we have solar plants connected to local distribution, local AC grid at 20 kV, or wind power plant connected, stepped up through suitable step-up transformers connected to a 100 kV utility grid, and then in turn it is again stepped up and connected to a 220 kV utility grid or to a local distribution network. So here if you see, the function of the energy storage system is integration of renewables. They generally plan from 1 to 100 megawatts, and they can give from 1 to 10 hours. That means this energy storage system, along with this renewable energy system based generation stores, power generation plants like solar or wind, they give together a stable power output instead of a discontinuous power output. That's the purpose of this energy storage system application in that particular location. That means we can plan energy storage systems at various points in the utility grid or the distribution grid, but each function has to be designed for a particular application. Now, at the beginning of the distribution network, that is network, we have energy storage systems. We generally 1 to 50 megawatts, and from 15 minutes to 1 hour, this energy storage system will be designed to supply the power and energy. Next, at the distribution level, here they are having 20 kV. Here we have 11 kV or 33 kV nowadays. 11 kV is generally our network. Energy system or postponement of grid update, and they generally plan 1 to 10 megawatts in 6 hours. So the idea is to avoid the increase of transmission line capacity by using a local power source to meet the peak powers. That way, the total transmission network capability can be reduced. And in the case of load end, that means at the point where the load is connected, heavy industries or any other loads are connected to the distribution network, energy storage system can be installed, and the application will be for peak shaving. That is, the maximum demand drawn by the load can be reduced by putting energy storage system, and the power generally they are designed is 0.5 megawatt to 10 megawatts, and for about 1 hour duration. So these are the applications of energy storage systems in utility grid. And this last one, where you have got connected to industry distribution network, it is also a microgrid if you have a local distributed energy source integrated into it. Now, next section, we will see illustration of typical battery energy storage system for Indian microgrid applications developed for commercial supply. Now, energy storage systems in solar power plants, they are basically connected in two topologies when they are integrated with the utility grid or microgrid. Common DC bus topology. This is the common DC bus topology where we have, for example, a solar power plant connected to the DC bus to a DC-DC converter. So this DC-DC converter both supplies the power from the solar power plant panels to the DC bus, and also it has got the power function of it has got the function of converting the variable power output, voltage output and power output of the solar arrays into a fixed DC output, and it's connected to local DC bus. Here we have to the local DC bus connected energy storage, the battery, which is connected through a DC-DC converter to this local DC bus, and together when this DC bus is connected to DC to AC inverter that is connected to grid or a microgrid. So the DC input to microgrid has got various sources connected to it, PV power plant and energy storage system. Next, this is a DC bus topology, it's called. Now here we have for this DC bus topology can be applied in AC, mostly in microgrids, and here the AC bus topology, if you see here, a solar power plant is connected to an AC bus, like we have seen other application earlier slides. A DC to AC converter is there. This connects to the local AC bus, like something like 415 volts or 6 kV. Now here you can have also an energy storage system which has got a power converter which converts the DC to AC for supplying power from energy storage to grid. And if you want to charge the batteries, then you can use this AC to DC converter for charging the batteries. So this will be a bidirectional converter. Now this AC bus can see this solar power plant along with the DC energy source integrated with the energy management system, a single power source, and feed to the AC bus. So this is a common method, AC bus topology for utility bus connection. So a typical example of a battery energy storage system for renewable energy applications developed by one of the Indian Maharatna companies. In fact, it is our BHL corporate R&D which developed it. I cannot put the slide here fully, so I am showing it. Now we can see why energy storage systems. Energy storage systems enable time shifting between electricity generation and for various applications. We have seen in our earlier slides in the big power system how it is possible to develop energy storage system for various functions required and applications required in a large power plant, power system, utility grid network, or in a microgrid network. So these are various things which we have already discussed. I'm just showing the slide and then going ahead. Hello, are you able to see this slide, please? Hello, are you able to see
sir.
this slide?
We can able to see the only the block diagrams.
No, that means again I have gone through my slides and you are not seeing my slides. This is not. Is it able to show introduction why energy storage systems are there?
No, sir.
So something is happening. I don't know how to make. This is the problem with virtual seminars. Okay. I've been telling something and right. Okay. How to manage this particular thing? I don't know. I'll show one block diagram.
Yes, sir.
Tell
now,
me if it is.
Now we can able to see the introduction section.
Okay. Typical development project of energy storage system. Battery energy storage system I'll show which our BHL R&D developed for a solar power plant. Now please see these slides. If they don't change, please tell me, because I'm not seeing what you are seeing. I'm only seeing what I am presenting. That's the problem. Okay. So one of the coordinators keep continuously monitoring the things.
Oh, okay.
Typical development battery energy storage system with 3 types of batteries, total energy of 1 megawatt hour with 500 kilowatt solar power plant for following applications they have developed. Capacity firming, time shifting of energy consumption, load leveling, ramp rate control of renewable energy generation. Now slide change. Are you able to see the slide change? Single line diagram.
No,
are able to see?
Single line diagram, sir. Of typical.
Are you able to see that?
Yes.
Yes. Okay, block diagram. So this, if you see, it shows that the utility grid, local utility grid is 6.6 kV AC bus, and it is already connected with the solar power plant with the PCU and a step-up transformer for 320 volts to 6.6 kV to the local AC 6.6 kV 6.6 kV AC bus. So there's an existing 500 kilowatt PV plant, solar PV plant. Now we developed this energy storage system to see that the fluctuations in output of the solar power plant are minimized, and they're also meant for certain purposes which we already told earlier. Now it has got an energy management system. It is called SCADA, which controls the functions of output management from solar power plant and the energy storage system. Now here the energy storage system consists of 3 types of battery banks: battery A, battery B, battery C. Battery A is a lithium ion battery. Battery B is a advanced lead calcium or lead carbon battery. Battery C is vanadium lead oxide flow battery. Here each battery is connected to a bidirectional converter, as I illustrated in the previous slide, through a step-up transformer to the AC bus. And within this energy storage system, there's a local AC bus of 415 volts, where each battery bank is connected to a bidirectional converter to the 415 volt AC bus. So here, lithium-ion battery through a bidirectional converter connected to the 415 volt AC bus. Similarly, a battery bank B, that is lead carbon battery, advanced lead carbon battery, connected to a bidirectional converter through to the local AC bus. Then third battery bank that is using the batteries, vanadium redoxide flow batteries. These are the advanced batteries, and connected through a separate bidirectional converter to the local AC bus, 415 volts. All these are connected from here, 415 volt AC bus to the 6.6 kV AC bus. The functioning of all these is controlled through energy management system integrated in this SCADA system. It also does protection, monitoring, and data logging, everything. So the purpose of this battery bank is to see that the solar PV plant along with this 1 megawatt electric battery energy storage bank, together they give a constant power to the 6.6 kV AC bus. I think in this case they have attempted to give around 500 kilowatts to the AC bus. Proposed applications, capacity firming. Now in this application, hello, are you able to see the slide change? Hello, coordinator.
No, sir, we can able to see the only single line diagram, sir.
I think every time I have to go to the slide and then do it. I don't know what is the situation. Now, proposed applications, are you able to see?
Hold on for a minute. 1 minute, sir. Yes, sir. Now there is a slide change.
So proposed applications, capacity firming. The purpose of this project was to meet certain application requirements, that is capacity firming. Are you able to see the slide which names applications?
Proposed applications, sir.
Are you able to see that?
Yes, sir.
So this slide I'm explaining now. Capacity firming, in this application, the battery energy system will be controlled such that net power from the 500 solar power plant with 1 megawatt electric battery bank will be exported to grid at a predetermined power level for a given duration. That's the purpose. The benefits of that is establishment of energy storage system technology for mitigation of intermittent nature of power generation from renewable energy storage sources. Then establishment of battery and storage system technology with the different types of batteries with merits and demerits of each one. This will give experience in design, operation, maintenance of battery energy sources with different types of batteries and also with battery hybrid sources. Now, okay. Now, next slide, are you able to see proposed applications? Hello, coordinator, please.
Proposed application 1, sir. We can only be able to see proposed application 1.
I don't know. There is some problem with the website, or because my signal here is quite good, that broad bandwidth. Okay, again I have to upload, I think. Now proposed application 2, are able to see?
1 minute, sir.
Okay, I think I'll go to, there are 2 more slides. If I complete this, then we'll go to the type.
Yes, sir. Proposed application.
Technologies. Application 2, you are able to see?
Yes, sir.
Okay, the purpose of this project was to meet another application, find this time shifting of energy consumption. In this application, energy generated from 500 kilowatt solar power plant will be used for charging the battery during daytime, and the same will be used for feeding to the local load of 200 kilowatt for 5 hours during night time in the campus of corporate R&D of BHEL in Hyderabad. The benefit envisaged is establishment energy storage technology system technology for time shifting. So you have seen here what is this energy storage system is able to achieve. Solar power plant, as we have seen in the previous slides, only now you want to give the power from the solar power plant up to 8 o'clock. So time when you feed the save it and give it to the local loads. That means you are not drawing the power from the grid during that extended period of energy fed from the energy storage. So this saves the costly energy purchased from the utility grid. So this is another major. The same technology used for islanding applications. That means when the utility grid fails, this particular energy storage system will be able to power from the local energy source and feed to the local load. So this illustrates the various functions of energy storage systems in microgrid as well as utility grid. Are you able to see the application coordinator, please? Hello?
Yes, sir.
Are you able to see the third proposed application for three?
No, sir. No, sir.
Proposed application 3, are you able to see? What are you seeing on your screen?
Now it is a slide change, sir. Now we are able to see the proposed application 3, sir.
Okay. Then the another function of this particular energy storage system development project was it's able to give load leveling. In this application, the maximum power drawn from the BHEL R&D campus will be limited to predetermined values with the battery energy storage system along with the 500 kilowatts solar power plant. The benefit that's achieved by this implementation in this particular project is establishment energy storage technology for load leveling and peak load shaving. That means the maximum power requirement drawn from the utility grid is reduced. So as you know, electricity discoms levy a tariff on peak load demand you have utilized, and that is reduced by using energy storage system. Right. Next section will deal with energy storage technologies. Okay, I'll quickly go through here various. Coordinator, please be online continuously. You
Okay,
should tell me. Now, this is an important slide. Energy storage system technologies are classified based on their type of energy, primary energy.
Yes,
so
sir.
this classification is given based on a white paper on electrical energy storage in the International Electrochemical Commission in 2011 December. So mechanical type of energy storage systems are pumped hydro storage, then compressed air energy storage system, then flywheel energy storage system. Then we have electrochemical energy storage systems, battery energy storage systems, flow battery energy storage systems, then chemical energy storage systems are hydrogen fuel energy storage system. Then we have electrical energy storage systems, superconducting magnetic coil. Then we have thermal energy storage systems or thermal storage systems like hot springs and other things. Okay, I'll again change every slide this way. Now here, if you see this again, another representation of the same thing in a pictorial form in a block diagram. You see, this is again another pictorial form. We'll quickly go to the classification energy again. In the electrochemical, are you able to see this slide? Classification of energy storage system.
We
now you see.
We are in a 61 slide, sir.
Now it's 63 slide. Classification energy storage system, electrochemical. So here you have primary batteries, secondary batteries, acid, lithium-ion, and flow batteries. Then mechanical, pumped hydro, flywheel, compressed air. Chemical we have seen. All these are again shown in picture. Now we are going to talk in this presentation focus on battery energy storage systems. Now we have seen the advantages of energy storage systems in utility applications. They are mainly used for load leveling, improving power quality, diversifying generation portfolio, enhancing safety and reliability of power supply. That means continuous power supply you get even if the main utility grid fails. Increased efficiency of electric generation. That means you reduce the peak power drawn from the transmission lines, thus deferring expansion of the power system infrastructure, lowering the operational cost of power generation while saving electricity expenses from. That means you are trying to take the cheaper renewable energy based power generation, which is cheaper in many large scale applications. Mitigation of system fluctuations, low and high frequencies, acceleration of synergy between electric vehicles and electric grid. I'm not going deep into it, but just see it. Now, these are the major important battery installations made worldwide. I'll quickly go through it. Sorry, this is different types of Okay, this is a slide I wanted to show. Now these are the various lithium-ion battery energy storage systems already used in world, and it illustrates that we are far behind, but we are trying to catch up. These are not new to the world. They're already installed right from 2012 I am showing up to 2016. They are 32 megawatts for half an hour, for 15 minutes energy supply. Location is US, California. Similarly, we have 25 megawatts. Worldwide, they have China 3 megawatts, then 8 megawatts California again. Then applications and functionality you can see here. The slides are shared with you. You can take it and see it. 2014 they already installed, and Korea also they installed 1 megawatt for 10 hours in 2015. And the application functionality will show whatever we have discussed so far, like various functions for which the energy storage system is designed. In Germany also they made, and that is 1 megawatt 2015 for frequency regulation, renewable capacity farming, transmission upgrade due to wind, all those things. Again in 1 megawatt in US in 2016, this is for electric energy time shifting, frequency regulation, renewable energy time shifting. So this slide shows various functions for which they are used. Now I'll go to another slide, the comparison of various energy storage technologies. Coordinator, are able to see this slide, comparison of various storage technologies?
No, sir, we are on this. Yes, sir. Now we can able to see the slides.
Comparison of various storage technologies.
Yes, sir. Table.
Yeah, that we are, as we have mentioned, we are going to focus only on battery energy storage systems. In the battery energy storage systems, there are different types of batteries. Among them, most widely used till today is, or till many years, is lead acid. So now there are a few factors which are important in selecting a battery. The battery energy density, power capacity, power density, and cycle life, cost, and various other issues. Let us focus on few things: power density, energy density, and cycle. Okay, cost is the aspect we'll see later. It is there in this slide, but I'm not going to discuss because of shortage of time. I think I have to go through fast. So lead acid battery is able to give a power density of 100 watts per liter, and most important thing is energy density. We will see that watt hours per liter is the important care. That means how much energy you can put 1 kg weight of the energy source. So it is generally shown as 50 to 80, but it's not that much. This is theoretical maybe. It is generally around 30 to 40. We will see another slide, other slides. So this is the benchmark. Now if you see the cycle is something like 200 to 1800 cycles. One cycle is one charge and one discharge. So we'll go to the lithium ion one. So energy density here is almost 4 times. So it is 50 minimum, here 200 watt hours per somewhere here. This is marked as L. It is not L. It is, please read it as energy density unit as watt hours per. So this will 200 to 500 watt hours per kg, and life cycles, if you see here, they are coming up to 1000 to 2000, 20,000 life cycle. That means 10,000 to 20,000 charge and discharge cycles. Now other things, this technology, lead acid is mature. These are all lithium ion available. Another important technology that is there in batteries is sodium sulfur. Again, this is high energy density, 150 to 300 watt hours per kg, and it gives us a life of around 2,500 to 4,000. But this is much less than and this is also available commercially. But the main disadvantage of sodium and sulfur batteries are they are high temperature batteries. That means they don't operate room temperature. They need auxiliary system for heating up. Then we have nickel cadmium. This you can see the comparisons, but they are not now being used because of some the disposal of the battery, that is environmental issues are coming. So people are using maximum lead acid and lithium ion. Then new generation batteries which are coming up are vanadium redoxide batteries, flow batteries these are. And these have what the advantage of these batteries is the power and energy are independent of each other in this. Power is what this power pack can supply. For example, how much maximum current at a constant voltage at a given voltage the particular power pack can supply. Battery power pack is the power, voltage into current. Now how much time this power can be supplied is energy. In case of lead acid and other things, the electrolyte and the design of the battery decides how much energy density. Whereas in the case of vanadium lead oxide flow batteries, both are independent by the conception and principle of operation. I'll show a video on that. It will be very illustrative. So these are the new type of battery which world is working. And our Indian academic institutions also should work with these batteries, energy storage systems. So this has got whatever per kg has 25 to 30 energy density, but this is on what benchmark we had to see. And the life cycle is 12,000 plus, and this is still evolving. Commercially, they are available. As I showed in the previous project developed by our BHL R&D, we used one vanadium dioxide flow battery of about 200 watt hours. Now, this is another typical example of another storage system other than battery, which I found recently our Indian developers are also commercially being supplied. They are developing. This is by Greenco, and other one is this is a what do you call hydro energy based hydropower. Hello.
Yes, sir.
Coordinator, are able to see this slide with the
Yes,
solar storage? Okay.
Tariff and spell. Yes, sir. Yes, sir.
Now, this is pumped storage. That is what pumped hydro it is called. Here, what they are doing is they use the hydro energy during power generation and pump it back to the storage tank during the non-requirement using solar energy supplied pumps and other things. So this is what we have seen in mechanical pump storage. This is an application of that, and India already is working on it. This Greenco company and another Renew Power are able to quote for this to government to supply 300 megawatt capacity pump storage, battery energy storage, and also Greenco is supplying is quoted with 100 megawatts pump storage and 800 megawatt pump storage. So these are all hybrid energy storage systems. More details you can go into the literature I have given. Now we are going to details of various battery energy storage systems. See, if you see this is the internal structure of chemical structure of lithium ion battery. I'll just take you quickly to a video which will present the principle of operation and other advantages of lithium ion battery. Hello, coordinator, are able to see this slide?
Yes, sir. Lithium ion battery, sir.
Are able to see the slide of video I'm presenting?
No, sir.
Okay, I will change I'll again close the stop sharing, then open sharing tray. I'll go to this. Now are able to see the presentation. Coordinator, please come online.
1 minute, sir. No, sir. No presentation and no screen sharing, sir. Yes, sir.
Now?
Yes, sir. Now we can able to see the video, sir. YouTube.
Okay. YouTube presentation, if you're able to see.
Sir, we cannot able to see audio and video, sir.
Okay.
Yeah. Yes, sir. No, we can able to see the video, but not the audio, sir.
I think again the previous problem while uploading.
You should include the audio, sir. System audio.
Very first cell, developed by Alessandro Volta more than 200 years ago, was based on the concept of electrochemical potential.
Yes, sir. Now we can able to hear the audio.
Chemical series is shown here. According to these values, lithium has Tesla cell out from the battery pack and break it down. Tesla, with the help of lithium-ion cells, solved this issue, and why lithium-ion cells are going to become even better in the future. Let's take a Tesla cell out from the battery pack and break it down. You can see different layers of chemical compounds inside it. Tesla's lithium-ion battery works on an interesting concept associated with metals called the electrochemical potential. Electrochemical potential is electrons. In fact, the very first cell, developed by Alessandro Volta more than 100 years ago, was the concept of electrochemical potential. A general electrochemical series is shown here. According to these values, lithium has the highest tendency to lose electrons, and fluorine has the least tendency to lose electrons. Volta took two metals with different electrochemical potentials, in this case zinc and silver, and created an external flow of electricity. Sony made the first commercial model of a lithium-ion battery in 1991. It was again based on the same concept of electrochemical potential. Lithium, which has the highest tendency to lose electrons, was used in lithium-ion cells. Lithium has only one electron in its outer shell and always wants to lose this electron. Due to this reason, pure lithium is a highly reactive metal. It even reacts with water and air. The trick of a lithium-ion battery operation is the fact that lithium, in its pure form, is a reactive metal. But when lithium is part of a metal oxide, it is quite stable. Assume that somehow we have there. The electrolyte between the graphite and the metal oxide acts as a guard which allows only lithium ions through. Now let's see what happens when you connect a power source across this arrangement. The positive side of the power source will obviously attract and remove electrons from the lithium atoms of the metal oxide. These electrons flow through the external circuit as they cannot of its microporosity. In a practical cell, the graphite and metal oxide are coated onto copper and aluminum foils. The foils act as current collectors, and the positive and negative tabs can be easily taken out from the current collectors. An organic salt of lithium acts as the electrolyte, and it is coated onto the separator sheet. All these three sheets are wound onto the cylinder around a central steel core, thus making the cell more compact. A standard Tesla cell has a voltage of between 3 and 4.2 volts. Many such Tesla cells are connected in series and in a parallel fashion to form a module. 16 such modules are connected in series to form a battery Tesla car. Lithium-ion cells produce a lot of heat during the operation. and a high temperature will decay the cell's performance. A battery management system is used to manage the temperature, state of charge,
So now I'll be going to the next slide. Hello, coordinator, please. Coordinator.
Yes, sir.
Oh, okay, I am cutting short the video because of the time management. So others can see, those who are interested, they can see from the notes I'll be giving these links. They can see in the internet and more details. The basics of how these lithium-ion cells, latest Tesla battery lithium-ion cells, lithium-ion battery works, I have demonstrated here. So other things you can understand. So the advantage of lithium battery we have seen in the tabular form. Functionality we have seen in the video and in this PPT. Now I'll selection of batteries for few applications. I'll show one slide and then go to other batteries. Now here, coordinator, please see if you are able to see my slide. Selection of batteries for few applications.
No, sir.
No?
No, sir.
There seems to be some, I don't know what's the issue. Hello? Now?
No, sir. We can only be able to see the YouTube link, sir. YouTube page.
And I will, okay, I have to again go back to the stops and go to this, I think. Now are you able to see that? My PPTs are able to. Hello?
A little lag, sir. Please hold on for a minute, sir. Yes, sir.
Okay, selection of batteries.
Selection of batteries.
Few applications.
Yes.
So I'll just, there are only a few more slides that you can. Selection of batteries for PV applications, key factors. So how do we compare batteries for best candidate for PV applications? Now, in the next slide, we'll see a Ragon plot available for batteries. This is slightly different from Ragon plot of earlier applications. So this shows the comparison between various battery technologies in terms of gravimetric energy density and volumetric energy density. This is what I told you, watt-hours per kg and watt-hours per liter. Okay, if we compare battery technology based on both the energy per volume and energy weight, we can see that lead acid batteries have less energy density than lithium-ion batteries. So this is the basic gist of it. I don't want to go deep into it because of time issues. Now, there's a trade-off between selecting these batteries. There's another video is there which shows all these details, but I'm now present time schedule and then showing that this can be selected based on the optimum selection of batteries for our application. Like, you know, Ragon plot shows, this is the Ragon. Are you able to see this graph, this block diagram? Coordinator, please.
No, sir.
Energy density of lithium-ion batteries?
No, sir.
Okay.
We are still at the previous slide, sir.
Okay. Now let us see if it has changed or no.
Yes, sir.
Now?
Yes, sir. No, it is again.
I have to back to the not a full screen mode and then come back again. At least that's working. So energy density of lithium-ion batteries and other batteries is compared here. If you see the volumetric density, that is watt-hours per liter, and gravimetric density, watt-hours per kg. If you see here, lead acid is a nickel metal hydride. Then we have lithium-ion batteries. Then thin film lithium. Mostly we'll be using lithium-ion batteries. So the advantage here is for a given volume and energy density, the highest you have is best choice you have lithium-ion. But in the market, the cheapest are lead acid. So are you able to see the next slide?
No, sir.
Okay, I'm going to the. I'm not going into the sodium sulfur one. Now you see here, this. Now are you able to see the redox flow battery chemical structure?
Yes, sir.
Yes.
Yes, sir. Yes, sir.
So this is the advanced battery which I was referring earlier in my talk. Here, if you see, there is a fluid inside the two tanks. So this is the electrolyte, and there is a cathode, and so positive half cathode, negative anode, and this is negative cathode and anode is there, and they are separated by the standard format of electrolyte. Instead of fixed quantity of electrolyte, the electrolyte is circulated through two pumps on one side of a membrane, and another side also it is circulated. So there is a permeable membrane which, like any other battery, it allows the exchange of ions and electrons. More details we'll see in this video, and it will explain you the details. Okay, let me see. Again, I had to change format. Oh. Again, I have forgotten to put that link. Okay, include system audio. Coordinator, are able to see the screen of my hello, coordinator?
Sir, no, sir.
Not able to see my screen?
No, sir.
Of now? Wait a minute, presenting is showing. Now, are you able to see my video screen?
Flow battery consists of.
Yes, sir. Now we can able to see the screen, sir.
Okay, you're able to see the screen, no?
Yes,
of the
sir.
video,
Yes.
YouTube video. Okay.
Yes, sir.
The Schmid vanadium redox flow battery consists of two tanks storing vanadium analyte and catholyte. Pumps are used to flow these electrolytes through adjacent half cells separated by an ion exchange membrane. Within the half cells, the electrolytes are chemically oxidized and reduced to reversibly convert electrical to chemical energy. An external electrical power source like PV installation supplies the energy to charge the vanadium redox flow battery. The two vanadium electrolytes are flown through the cell stack in which the electrical energy is converted to chemical energy. The electrolytes charged within the cell are flown back to the tanks, increasing the battery's state of charge. Looking into the cell at the molecular level, vanadium-3 and vanadium-4 enter the electrochemical cell. At the catholyte half cell, the vanadium-4 is oxidized to vanadium-5. This chemical reaction yields an electron, which is drawn off by the conductive electrode material, and a hydronium ion, which diffuses across the membrane to the opposite half cell. At the anode half cell, the electron, which has traversed the external circuit, reduces vanadium-3 to vanadium-2. The hydronium ion, which has passed the membrane, balances the overall charge of the half cell. The two electrolytes leave the half cells in a charged state as vanadium-2 and vanadium-5. Once the grid cannot provide energy to the battery system, the vanadium redox flow battery swaps to discharge. Vanadium-5 and vanadium-2 ions carry the chemical energy into the cell stack. The chemical energy stored within the two electrolytes is converted to electrical energy, feeding the external load. At the molecular level, the reverse of the charging reaction occurs. Vanadium-2 is oxidized to form vanadium-3, releasing an electron which carries the electrical energy. For charge balancing, a hydronium ion crosses the ion conductive membrane. Vanadium-5 is reduced by an electron under consumption of a hydronium ion. The electrolytes leave the cell in their discharge states in the form of vanadium-3 and 4. The vanadium redox flow battery delivers electrical power until the electrolytes within the two tanks are completely discharged. The Schmid vanadium redox flow battery can be independently scaled for appropriate power and energy. Power can be adjusted through cell size and number. Energy is defined by the tank volume to perfectly meet the customer's needs. As the electrochemical reaction takes place in the electrolyte solution, no loss in power or capacity takes place due to side reactions as observed in conventional batteries. This fact ensures lifetimes superior to any other electrochemical storage. Even deep discharge does not influence battery health. Unlike other flow battery types, the all-vanadium redox flow battery incorporates vanadium in both electrolytes, eliminating battery deterioration through cross-contamination. The composition of the electrolytes, vanadium salts solved in dilute sulfuric acid, guarantees low hazard potential and best possible ecologic properties. With all these benefits in cooperation with low production costs, the Schmid VRFB is the appropriate means for renewable energy storage. Consists of 2 tanks storing vanadium analyte and catholyte. Pump.
Coordinator, are you able to see my slide?
No, sir. Yes, sir. No, we can able to see the slides, sir. Redox flow battery.
I will just I'll skip some slides and then you can see them later. Okay. So the major features of, you have seen how the redox side flow battery works and internal descriptions of how the electron exchange takes place. Now let us see the major features of redox side flow batteries. Compared with rechargeable batteries, lead acid and lithium ion, commercial redox side flow batteries, RFB means redox side flow batteries, currently have low energy density. However, they show several distinctive feature advantages. Redox side flow batteries, power and energy capacities are completely independent of each other. This is what I was explaining earlier also. The power is determined by the stack, while the energy capacity is determined by the electrolyte. Redox side flow battery is thus easy to scale to multi-megawatt level and megawatt hours by modular design. This is what that Schmid module integration video is on the redox side flow batteries. It can be expanded in capacity. So the redox side flow battery can be easily scaled up to multi-megawatt and multi-megawatt hour by modular design. And furthermore, requirement of redox side flow battery management, especially the equalization circuit algorithm against cell variability in the state of charge and temperature, are substantially lower than that of other batteries. Because the electrodes of redox side flow battery provide only an electrochemically active surface for redox reaction and only liquid phase reaction during charge and discharge, flow battery chemistry has an exceptionally long calendar life, that is lifespan. For example, a vanadium redox side flow battery has been verified to withstand more than 2 lakh cycles and over 10 years in demonstrated project in Japan and Europe respectively. So this show a very promising potential in energy storage systems for utility applications, both in microgrid as well as utility grid. There is no metallic dendrite. These are all internal issues. Redox side flow batteries exhibit transient behavior with very fast response speed. The switching time between charge and discharge is often less than 0.02 seconds. It is therefore well suited for balancing highly variable renewables. So this is the advantage of redox side flow batteries. I'm not going into the other details. Various installations have been done with this. Coordinator, are you able to see this slide? Red oxide flow battery illustrative example of installations. Hello. Hello,
Yes, sir.
coordinator.
Yes, sir.
Are you able to see this table?
No, sir. Redox flow battery, sir.
Okay. Now we see. Just tell me. I think a few slides are left.
Yes, sir. Now we can able to see the table, sir.
So this slide shows typical installations of variable vanadium red oxide flow batteries. I could collect up to 2016. So they're already installed in various places like China, United States, and Japan. These are having a 2 megawatt, 4 megawatt hour vanadium red oxide flow battery. The application in the power system is for balancing wind and solar power. They were installed in 2011. Similarly, in China, we have 5 megawatt, 10 megawatt, coupling with wind power, smoothing, ramping, transient. It was installed in 2012. Then US, they have put 1 megawatt and 3.2 megawatt VRB. The function is for load shifting, frequency regulation, voltage regulation. This was installed. In Japan, they have put 15 megawatt and for 4 hours, 60 megawatt hours. This is for coupling with wind and solar power for frequency fluctuation suppression. So this shows that these are the various batteries. I am just showing you one last slide. Some more, but I'll conclude and show you what is the future after the lithium ion. Of course, there are various types of lead acid batteries with supercapacitor also merged with them. You see in my literature I have given to you. Then we'll go to last video and close with that. I'm not able to spend time on other issues here, which are the future trend in batteries. Now I'll open this last, and with that I'll close. Wait a minute. Another video I'm sure. Yeah. Coordinator, are you able to see the YouTube video, please?
No, sir.
For solar panels
Are you
and
able to
wind
hear?
farms have reached
Yes, sir.
all time
Hold on
lows.
for a minute. Yes, sir.
No, yes. Yes or no? I stopped
No,
the
sir.
video now.
No, sir.
Okay.
Yes, sir. Now there is a little delay, sir. Yes, sir. Now we can able to see the video and audio.
So the sun isn't always shining.
If, for example, it's a beautiful sunny day and we've got a superabundance of electricity,
Coordinator, are you able to
we can't use it.
Yes, sir.
The question of how to firm
We can able to
that is
hear.
Sound are
putting
able
their
to hear?
Yes, sir. Audio is clear, sir.
technologists in the industry. We need a good way to
Video
store
also
energy for
clear?
later. And the main option right
Sir,
now
there
is
is
lithium-ion
something
batteries.
about Windows, sir.
Pardon?
The power
Yes,
wall.
yes, sir.
And
Video
utility
also
scale
clear,
systems. The
Video also clear, audio also is clear. So shall I continue with this video?
Yes, sir.
Right.
Sir, one small request, sir. Could you please wrap up the session, sir? Already we consumed a half an hour, sir. Extra. Hello, sir.
Battery for the electrical grid, we need to look at a further cost reduction of 10 to 20x.
Right now, lithium-ion batteries just can't store more than 4 hours worth of energy at a price point that would make sense. Plus, they pose a fire risk, and their ability to hold a charge fades over time. To address this, there's a cadre of entrepreneurs experimenting with a variety of.
Now we're seeing flow batteries, which are liquid batteries, and we're seeing other forms of storage that are not chemical or battery-based storage.
And each has serious potential.
We looked at materials on the periodic table that were actually going to be cost competitive from day one.
Primus Power's flow battery is a workhorse.
Thermal energy storage has a pretty unique opportunity to be extremely low cost.
Our solution will last 30 plus years without any degradation in that performance.
Which technologies prevail remains to be seen, but one thing is clear. For renewables to truly compete with fossil fuels, we need to figure out a better way to store energy. From 2000 to 2018, installed wind power grew from 17,000 megawatts to over 563,000 megawatts, and solar power grew from a mere 1,250 megawatts to 485,000 megawatts. And it's not stopping there. Renewables are expected to grow an additional 50% over 5 years. Tesla, for example, built the world's largest lithium-ion battery in Australia, pairing it with a wind farm to deliver electricity during peak internal tanks, meaning the energy from the electrolyte and the actual source of power generation are
tanks, which every other flow battery has. Primus only
policy is a big deal, since it will make face the same problem with longer duration storage. 35-ton bricks up and down, depending on energy needs, in a process that's automated with machine vision software.
We have a system tower crane that's utilizing excess solar or wind to drive motors and generators that lift and stack the bricks in a very specific sequence. Then when the power is needed from the grid, that same system will lower the bricks and discharge the electricity.
This system is sized for utility scale operation. The company says a standard installation could include 20 towers, providing a total of 300
outside in the remote areas.
Then there's thermal storage. It's still an emerging technology in this space, but it has the potential to store energy for longer than flow batteries. Recently, Antora received funding from a joint venture between the Department of
In the residential and commercial areas, you're going to have a certain type of technology. A lot of it will probably be battery based. I think as you get to utility scale and grid scale, you're going to see some
cost of a first system is essentially astronomical.
California has done is another policy that many are advocating.
Actually long lulls.
With the right mix of incentives and ingenuity, we're hopefully headed towards a future with a plethora of storage technologies.
The future.
Okay, coordinator.
Yes, sir.
My presentation is over.
Yes, sir.
Okay.
Sir, thank you for delivering wonderful lecture, sir. In spite of technical issue, thank you for delivering, sir. I would like to invite Divya madam to give a vote of thanks to you, sir. Yes, ma'am.
A very good afternoon to one and all. I'm here to give the vote of thanks to Dr. P.V. Rajagopal, sir. Sir delivered an excellent lecture on microgrid RES and energy storage systems. And he discussed about the microgrid illustrations. And also he discussed about the energy storage systems in the microgrid and its applications. And also he delivered excellent lecture on energy storage systems in the utility grid and microgrid. And also he given the introduction about the expected all India desk curve. And also he explained about the impact of RE integration on utility grid. And he explained about the single line diagram of the typical energy storage system. And also he explained about the proposed applications in the energy storage systems. And he discussed about the various technologies which are used in the energy storage systems. And also he explained about the advantages of the energy storage systems. And sir, you given a very brief explanation about what are the various factors which we have to consider to compare the storage technologies. Thank you, sir. Thank you for delivering a wonderful lecture to us. Thank you very much, sir.
Thank you. Thank you for the opportunity, and thanks for the organizers to give me this extended time. And thanks to the participants for staying with me for so long. Thank you. I'm sorry for the disturbances and rather technical. Thank you. Thank you, one and all.
Thank you, sir. I request all the participants we are going to resume the session, next session in 2 o'clock after the lunch break.
Sir, good afternoon, sir.
Hello, sir.
Jagannath, good afternoon.
Good afternoon, sir. Am I audible?
Yes, sir.
Yeah. Okay.
Good afternoon to all participants. This is Krishna, working as a professor in advertising. I'm co-coordinator for this STTP program. My colleague Sirisha will be introduced about Jagannath. Sirisha, madam, please carry on.
Good afternoon, one and all. We cordially invite Sri A.V.L.K. Jagannath Sharma Garu, Deputy Electrical Engineer, Deputy Executive Engineer, APEPDCL, Vijayawada, to 1 week online STTP on recent trends in renewable energy sources and their integration to smart grid. Sir, today is going to share his research and practical experiences on smart grid technologies for better grid management with enhanced penetration of renewable energies. Sir obtained his master's degree from REC Warangal with specialization in electrical machines and industrial drives, BTech from JNTU Kakinada. Sir has more than 22 years of experience in the power sector of Andhra Pradesh. Sir is presently posted as Deputy Executive Engineer, Commercial, APCC, Vidyut Savda, Vijayawada. His present scope of work involves dealing with commercial matters in connections with power procurement from central generating station and transmission services of power grid, PGCIL. His past experience includes working as ADE HT meters in APEPDCL for 1 year. Also, he worked on deputation in State Energy Conservation Mission, which is the state designated agency under the provisions of Energy Conservation Act 2001. In this SDA, he worked as DGM for 2.5 years. Prior to this assignment, he worked as Deputy Director Engineering, AP Electricity Regulatory Commission for 5.5 years. He worked in the areas of operation and maintenance in power distribution wing, commercial reforms, regulatory affairs, and power purchase wing in AP power sector since 1997. His specializations are load forecasting, regulatory affairs, distribution planning, commercial issues, power procurement planning, energy audit of electrical utilities. He was also guest faculty to ESEI Hyderabad, CIRE Hyderabad, and staff training institutes of AP Power Utilities. Thank you, sir. Sir, we welcome you, sir.
Sir, please take over this issue.
Yeah, sure, sir. Yeah, am I audible? Hello?
Yes,
am I
sir.
audible, sir? Am I audible,
Yes,
sir? Yeah. Okay. Yeah. Thank you very much for the introduction given by Madam. At the outset, I thank St. Peter's Engineering College authorities, particularly Dr. Brahmaya Garu, for giving me this opportunity to come as a guest lecture, to give a guest lecture on this short-term training program. The topic for our today's discussion is smart grid technologies for better grid management with enhanced penetration of renewable energy sources. This is the last point. Last line is very important. Enhanced penetration of renewable energy sources. That is the actually the striking point. I request all the participants to interrupt me whenever you feel free, whenever you have any query. I think it is better, or shall we take up the question and answers at the end? Whichever is convenient to you, we can do that. Okay, na sir?
Yes, sir.
Huh? Okay. Yeah. Yeah. Coming to our discussion point, I would like to make this presentation or this lecture or whatever it may be is as interactive as possible, because my way is it's not only just telling it on one side. I think I always invite a lot of interaction. That is very much interesting. That is the way we can exchange views, exchange things, and exchange knowledge. That is my, because I am basically from a distribution company. I am presently working in power purchase activity at the state level, and this smart grid technologies, or whatever is a smart grid, what we are contemplating nowadays. I think we have been hearing this for the past 10 to 15 years. Earlier also some kind of automations, some kind of involvements are there, but the term as a whole is gaining momentum during these days. Presently, okay. Just the next slide, I'm just showing we are representing how a typical power system looks like. So it has generation. Generation is done at 11 kV level, and the generation at lower voltage gets stepped up to the transmission voltages. Nowadays, the transmission voltages are up to 800 kV. What we are seeing in our home, we are getting at 415 volts 3-phase supply, whereas the maximum voltage that is getting transmitted across the country in India is 800 kV DC voltage. AC voltage is 765 kV AC voltage convention is available. The generated power, as you are aware, all are electrical engineering students. The generated power gets stepped up to 765 kV or 400 kV, depending on the design or depending upon the capacity, depending upon the volume and all. And again, there are different transmission voltages. Certain power gets transmitted at 400 kV. Certain power gets transmitted at 220 kV. In similar lines, in it comes to 33 kV in a receiving substation in the distribution sector. So from that 33 kV, the 11 kV feeders are drawn up. 11 kV feeders are called primary distribution feeders because from where we get the power to the most of our consumers. Almost all consumers are covered under 11 kV and below. Only the bulk industrial consumers connected at 33 kV and above, 130 kV and 220 kV. There are only not more than 1,000 or 2,000 consumers across the state, across AP or across Telangana, that are connected at higher voltage levels. But most of the consumers are connected at 11 kV and below. So 11 kV is called primary distribution feeders, and after distribution transformer downwards, it is called a secondary distribution feeder. So from generation end to the end use at our home, or end use at in a commercial complex, or end use in an agricultural pump set, wherever the power flows, right from generation to, this is how the typical power system represents. This is conventional representation of a typical power system. So this can be termed as a grid, because there are a lot of the entire network, right from generation to the end use distribution. It is covered through different kind of voltage network, from 765 kV, 400 kV, 220 kV, 132 kV, 33 kV, whatever it is all represented as a meshed network. It's a grid. Everything is connected at a grid. Grid means it can have radial lines, it can have ring lines, it can have a meshed type of network and all. And depending upon the network topology, depending upon the usage, depending upon the scattering of lines required, that the grid gets developed over a period of time. Excuse me. This is the basic representation. In the next slide, is to understand how the entire power system operates, because every power system will have large generators, lot of consumer loads. They are got interconnected, and they have to operate at a constant frequency. As you know, whenever we synchronize a generator to the grid, the generator, all the generators operate at a single frequency, have to operate in a single frequency. And frequency is the basic parameter of controlling and monitoring of the grid operations. This can be represented like this, like a tandem bicycle, what we are showing, moving at a constant speed. And the red pictures, they are pulling the bicycle, and the blue ones are sitting in. So we can represent that the persons who are pedaling the tandem cycle as the generators who are moving the system, and all the persons sitting in blue colored one, they are the loads in the grid, and all these wheels and all that infrastructure is grid and network and all that. So blue figures represent load. It could be industrial load, private dwellings, or whatever it may be. And red figures represent power plants. And this is supposed to be operating in a constant speed. The speed at which the tandem bike is moving can be termed as the frequency at which the system is moving. Presently, in India, the standard is 50 hertz. In US, it is 60 hertz. Constant frequency standard. So not that entire time, during the entire time of 24/7 or all every minute to minute and second to second, the frequency will be maintained at a constantly at 50 hertz. There will be some deviations, but the deviations are very less. We are supposed to, as per the Indian grid standards presently, the grid has to operate at 49.9 hertz to 50.1 hertz. You know, it's a narrow band. The frequency of deviations, the bandwidth of deviations is very narrow, and the grid is expected to operate in such a narrow band. So grid frequency is one of the basic parameter of grid management. I will certainly tell you. There is another point is also there. Another parameter is also there, which is also critical in maintaining the grid security, grid stability, and helps in perfect operation of the grid. What is that parameter? Apart from grid frequency, system frequency, there is another grid parameter is also there, which is also almost equally important with regard to operation of the successful operation of the of a power system grid. Any guess? Hello? Hello, sir. Am I audible? Hello? Hello, sir. Hello? 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 Sir, Dr. Brahmay garu? Hello? Hello, sir. Hello? Hello? Hello, sir. Am I audible? Hello, sir. Hello, sir. Hello?
Hello.
Hello, sir. Any problem, sir? Am I audible?
Yes,
Hello?
sir.
Audible, sir.
Audible? Okay.
Sir, please continue, sir.
Okay. Yeah. As I am saying, the second most critical parameter in terms of grid operation is the, apart from frequency, it is the voltage, bus voltages at different substations. What we call in our literature, we call them nodes, but practically in field, we call them as substations. Bus voltages in different substations is also one of the important parameter of grid operation. And the bus voltages, they are determined by, they are mostly governed by the reactive power flow. Reactive power flow from one point to the another. Active power flow also affects the bus voltages from place to place, but the impact of reactive power flow in AC networks is very important in bus voltage, in maintaining the bus voltages. And as per the grid code conditions also, the bus voltages have to be maintained within the limits. Otherwise, there's a lot of constraints. The problems will come up in successful grid operation. The thing is that the purpose of the grid, grid is to supply reliable power, 24/7 reliable power to the end consumer. That is the basic need of the hour, and that is the basic requirement within which all the small networks are got interconnected into a bigger network. As at presently, the entire country is operating in a single grid and as a single frequency. Earlier, we used to have each and every state as a individual grid. Later, states got connected in a regional level. Now, all these regions, all the regions in the country, there are 5 regions in the country: southern region, western region, eastern region, northern region, and northeastern region. All these regions are also got connected, or got interconnected through a powerful AC high power capacity power corridors at 765 kV level. Now 1200 kV is also under testing. So in future 1200 kV system also may come in India. Presently, all these regional grids all are got connected with strong backbone network at 765 kV. So then we come to our discussion, what is a smart grid? Why the present grid is not called as a smart grid? What smartness is required in the present grid to become smart? What are the additional elements that are required? The present grids, the present conventional grids, they are called only just okay. They are able to meet the requirements of the consumers, present consumers, from generation end to the distribution end. But with the advent of new technologies, particularly renewable energy. So renewable energy has come in a big way, and it has a lot of potential to grow also in the coming years. With the advent of renewable energy technologies into the grid, with integration of renewable energy, high capacity renewable energy generation plants into the grid, the problems associated, they cause a lot of problems to the network. There are a lot of issues out there. Mainly renewable energy, what we say is renewable means mainly the wind and solar plants. Mainly the wind and solar plants, and small hydro, other kinds of renewable energies are also there, like biomass plants, bagasse plants, municipal solid waste, whatever. All these are all smaller capacity. But the integration of this wind and solar plants is very bigger when compared to any other renewable energy sources. Just a minute, I'm just we are discussing about what is a smart grid. So smart grid, there are large, if you see the literature in the internet, there are numerous number of definitions. What could be a smart grid like that? Because there is no standard definition or standard like that. It is a continuous evolving process. Basically, the smart grid is an electrical grid that uses information and communication technology to gather data and to act on information about the behavior of suppliers and consumers in an automated fashion. That means the requirements of generators and the requirements of consumers are to be met in an automated fashion using the latest communication technologies, information and communication technology. And the second definition is it is a digital layer in the analog structure of the electrical system, which can react to wide spectrum of abnormalities in the most efficient manner.
Sir, sorry for the interruption.
Hello?
PPT
Yeah.
is not shared. Sir.
Hello? PPT is not being shared, huh?
Yes, sir.
Okay. I will just share it again.
Teams is showing.
Yeah. Yeah. Is it now shared?
Yes, sir.
Yeah.
Yes.
Is it now shared? Yeah.
Yes,
okay.
Sir.
Okay.
Thank you, sir.
Thank you. As we are okay, just think of think of present grids. Present grid entails only one-way communication from generator end to the consumer end. The power flow is only one directional from generator to the power flows to the consumers through different transmission media, and the generators are controlled earlier 30-40 years back mechanically through a mechanical frequency meter. The engineer sitting in the control room making use of a mechanical frequency meter, electromechanical frequency meter. They used to control through telephone network and all, entire substations and all, generating stations and all. Now with some kind of an automation and some kind of a digital technology, now the control rooms are seemingly different. Now with the advent of communication technology, we are able to see the grid in a map, in a spatial map. We will see the grid on which line how much power is flowing, or which generator is generating how much, and what is the frequency, which district is drawing how much, and like that. In a spatial map, we are able to see what is the power flow on a real-time basis. And voltages also. As I said, the voltage is also a very important parameter in grid monitoring. This is also not called smart grid. We are started our journey towards smart grid, towards creating smart grid. Earlier grids, the conventional grids, they are only dumb grids. So there is no communication. Whatever is happening through an electromechanical means. There is no electronics intervention and all. So a smart grid can be defined as including a digital layer in the analog structure of electrical system, which can react to widespread spectrum of abnormalities in the most efficient manner. And the third point is a modern power